Hi, and welcome to my session at the end of this day. It's about geospatial analytics and how we're using Microsoft Azure to do our stuff. My name is Arno. I'm from Black Shark AI, and maybe just 2 or 3 words about who we are. We are an Austrian startup located in Graz with just about over 100 employees. And you might have heard our name in combination with Microsoft's Flight Simulator, where we were responsible for the world. So basically, almost everything that is on the ground was our work, whereas Asobo, the producer of the game, was responsible for the physics, the weather, the planes, and other stuff. Right now, as we realized, a digital globe is something that is of interest to others as well. We are working on an end-to-end platform where eventually, we are having synthetic environments like you see in the very last image here. So with that out of the way, what is this talk all about? Basically, we have satellite imagery, and this satellite imagery is in 3 bands, meaning RGB. So we are not using multiband like near infrared or other fancy stuff, just RGB. And we then would like to feed this image into one of our algorithms so that eventually we receive detected footprints. And this is what we are going to talk about in this session. So Azure Orbital Analytics was released about 3 or 4 weeks ago. It's basically Azure Space Team's reference architecture. So we were one of their guinea pigs and gave them early feedback. And so it's a reference architecture, meaning it's not a ready-made service. You have to do some parts on your own. What they are providing is basically some scripts to do the initial setup for you, but anything else is then on your side. It makes use of many things, of Synapse Analytics, which in turn makes use of data lake store of Apache Spark, Azure Batch, and container registries. For the last 2, we will see later on why. And of course, you need some imagery, right? So either you bring your own aerial or satellite imagery, or you have access to either Airbus or Maxar or to Microsoft's own planetary computer. Once everything is in place, you're ready to go and do some geospatial analysis yourself. So the first question that some of you might have is, why Synapse? Because Synapse is more like known for SQL, streaming data, and other stuff, whereas when we are dealing with imagery, it's not like that the satellite are directly streaming the images to us, but it's more like more like a batch processing, meaning we're dealing with huge amounts of data, typically in our resolution, which is 50 centimeter, meaning a single pixel is 0.5 meter by 0.5 meter. The Earth is about between 0.5 petabyte and 1 petabyte. So why use Synapse there? And the reason is actually Synapse is a very mature workflow engine. It's in general availability for some years already. It has really many different integrations. So if you have a diverse set of data sources, then actually Synapse makes a lot of sense. And of course, you can use Spark and so on, right? So basically, Azure Synapse is a nice wrapper around many tools and makes handling data and workflows easy. So maybe let's just have a first look about how it looks like. So once you have done the necessary setup, and I'm not going through the setup routine because then the talk would already be over, you're greeted with the home screen of Synapse. And on the right-hand side, you see we have a place where we are defining our data sources. We can write our own scripts inside Synapse. We have a way to run pipelines, which are under the heading integrate, and of course, monitoring and managing stuff. So as a very easy and simplified example, let's assume we have a storage account where there are some files, right? And of course, I have some storage account already here, where we have containers here on the Black Shark, and let's say tiles. We have already some files. And for our demo pipeline, let's assume that we would like to check if in this directory there are only PNG files in order to make sure that our later processing steps are able to process these files. So the task is read the directory, check if everything is a PNG, and if yes, the pipeline succeeds, and if no, then the pipeline should fail. Okay, so what we first need to do is we need to link this storage account to Synapse. And what we do here is basically we say, okay, let's link external data to Synapse. And as you see, it's this here is only about Azure internal services. So we are using the blob storage. I'm going to name this one here Tile Store. And whoops, for some reason, this input field is always highly lagging. Anyway, so next we're going to select the storage account name. And we already saw it's this raw data. And in the background, Synapse is already checking if we have the necessary rights in our role to access this storage account. If we do, then we are already ready with the linking to the data store. And it should be done, right? And it will show up here, or maybe we need to nudge Azure a bit. So here you see the tile store, which I just showed you previously with the tile directory. Actually, in order to use this inside the pipeline, what we need to do is we need to define an integration data set. Integration data set is the way Synapse talks to the outside world. And here you see that actually they have much more ways to talk to the outside world. So it's not only Azure services, but also, if you have your own setup of Couchbase or DB2 or some FTP server somewhere, Google BigQuery, or even, let's see, some Oracle, PayPal, yeah, whatever. So this is when you're using data from external services. What we are, of course, doing, we are using blob storage. And when we're doing a blob storage, this data set might actually just be a single blob on the blob storage, right? So it just, for example, might be an Avro file or a JSON or a CSV or a Parquet file. But we are dealing with image files, so they are not, they do not contain, rows or additional attributes. So I'm choosing the binary type. And let's give this a name. Let's say this is our tile set, and it's linked service. Here you're able to see the tile store, which I just defined previously. And then they ask me to specify the very file on the storage account. We're doing something a little bit different. We're not defining a single file, but we're just defining the directory, nothing else. Because we're not interested in a single PNG file, but in all PNG files residing inside that directory. And I would say we're done here. So what we've done so far, we have linked the blob storage, we have defined the data set, which in turn means now we are ready to do to define our first pipeline ourselves. And in the integrate tab, I select add pipeline. Maybe I'm going to do this on the side and this one as well. So this will be our pipeline to check all blobs. And basically a pipeline in Synapse is a sequence or graph of activities. So there are different activities, like, for example, you're able to speak to a Spark instance or do some streaming or Geospatial or whatever, or you do some move and transform with copy data or data flow, or for example, you're going to call out to an Azure function or whatever. What we are doing is we take one of the activities here, which is about, no, this was the wrong one, which is all about getting metadata. And what we are doing is, let's call this all blocks. As you're able to see, there is a description field, a timeout, retry, and other stuff, but we're not really interested in this right now. For the settings, now you see why we needed to define integration data set. For this get metadata, we define the data set where we would like some metadata from. And in there, okay, probably just a little bit too large. In there, we are we have the chance to define, or query the last modified or item name if the item exists at all. But as this is all about listing the contents of the directory and not the name of the directory or when the directory was last modified, which of course some of you might notice when we are dealing with the blob storage, actually there is no directory, it's more like a prefix. But what we're really interested in are the child items. So with this, we already have defined our first activity, which is list all the child items of this data set, which in our case is a storage account where these PNG files are residing. And then we would like to check if all of them are PNG files. So what we are doing is actually, let's have a loop where we're now iterating over all items that we receive from the metadata. The for each is, so basically this is for each blob. What we do is, there are some additional parameters in order to see if we're able to do this sequentially or in parallel. And what we would really like to do is add the result of the list blobs. And as you see right now, we only have access to some system variables and to functions, but not to the output before. And the reason is, right now, these two activities do not depend on each other. So if I say this for each should depend on the get metadata activity, then if I go there again, you should see that we have access to the outputs of this other activity. What's important to understand or know is that actually the arrow here does not mean that this is a data flow. So there is no data flow going from the previous activity to the next activity, but it's a dependency. For each will only be executed once get metadata has finished its execution. And for this reason, when we say, okay, so what would we like to iterate over? It's the output of this previous activity. And as we were only doing the child items, we're only interested in the child items. So what we have defined here is basically the for each loop should iterate over all the child items which were the result of the list action. And then, of course, the question is, what do we do with each single item inside this for each loop? And this is where we are able to define additional activities. So once we're here, we're switching to a new view. And let's, for the purpose of this demonstration, let's make it easy, meaning let's have a simple if, which says if everything is okay, the pipeline succeeds. And if one item is wrong, then the entire pipeline should fail. For this, we need an if condition. And if this is a PNG. And again, we need to define what is the expression we would like to evaluate. And then we define activities for the true case and for the false case. So the activity which we are going to define is either we have access to the current item of the loop, but what we actually would like to do is, let's have, we would like to check if it's a PNG, and we make it easier on ourselves. We just check if the name of the blobs ends in .png. So we check with the activity or function ends with, and in there we say, okay, does the current item and the item that is returned by the get metadata activity has a name and a type, and we're only interested in the name. Does item name end with .png? This is the expression we're going to evaluate. And if it's true, we know it's a PNG file. If it's false, we know that something is not a PNG file. So for the true case, we don't need to take any action at all, because then everything just succeeds. And let's say for the false case, I think there is a fail activity where we say, okay, this is not the PNG. And we need to have a fail message, not the PNG file, and an error code. Let's see, something like this. Apparently, it does not like my name. What's wrong with my name? Okay, apparently here it doesn't like the space for whatever reason. Okay, so this is my fail activity. So inside our if true, we do nothing, and if false, we're failing the pipeline. Let's just make a commit of this. So we have a very simple pipeline where we first list all of the blobs. Then for each item in this list, we're evaluating the expression of our if activity, and if false, then we fail the pipeline. We have not defined any triggers, like, it would be able to say, a new file arrived, let's have this as a trigger. So I'm running it manually in the debug mode. And what you see here is it's listing all of the blobs. Let's refresh, because I'm sure it's already more or less finished. And what you see here is the list blobs activity finished successfully. The for each apparently was still running a bit. And then we evaluate this if clause for each individual PNG. Some of the activities have an output or an input and output. So for example, this list all blobs has, I'm not sure if you're able to read this. There is the reference to the tile set, and the output basically was the list of all the PNG files here, and some metadata about how long it took. For the for each, the output of the for each is only how many items we looped over. So there is no way to say, and for each is returning other results. And then we have if, and the if activity itself, in that sense, has neither input nor output. Okay, so everything was fine. We only have PNG files. So let's assume we would like to do a little bit more. Let's see what happens if we actually fail. So let's say I just do this by writing something which I'm sure where the expression is going to fail. And let's run this once more. And what we now should see is that the pipeline is failing. Maybe I do a refresh to make it a little bit quicker. And what you see now is our list blobs succeeded, but all of this, not the PNG, this was the fail activity. Of course, it failed. This is the reason for the fail activity. But in turn, each if condition failed because one of its inner activities failed. And now the for each failed because one of its inner activities, in that case, one of the ifs failed. So this is why then the whole pipeline fails. So yeah, this is basically how you define a workflow in here. Maybe just in order to show you, if we would like to define some variables, let's say we would like to have the fail message, because right now the fail message only says blob is not a PNG. Maybe we would like to have the real file name in the message, and the problem is that this that the current item is only available to activities that are a direct child of the for loop. So it's not available inside these false activities. And the way around this is that we define variables, for example, a variable named current blob. And then inside here, we set the variable here's a current blob to the expression item name. So in this way, the item name is inside the variable. We make a dependency here so that we have access to it. And now inside the false activity, we can use something like functions string a concat, like we'd say wrong blob format, and we use not item, but the variable. Where is my variable? There, the variable current blob. And in this way, we're able to have the name of the blob. And there is an error because you're only allowed to use single quotes and not double quotes. Now we have a way to have the failing name inside our error message. So this is, for example, how you have the ability to do additional variables which are passed across different activities. And now let's just do a refresh because it's faster. Now you see it says wrong blob format, and we have the name of the file. Or hopefully here, which is also the same. Okay, so basically, this is how you define your workflows. And this is all we need from Azure Synapse. So we are not really dealing with the SQL part or the more sophisticated data flows right now. We just need to define some pipelines. So maybe back to here, just as a reminder, this is what we try to achieve, right? Satellite imagery, machine learning magic, detected footprints. And from a bird's eye view, what we're doing is Synapse is at the core of our work. We're using some Spark stuff and also the batch account. We have our data in a source data lake store and store the results in a result data lake store. The imagery we have is stored in the first one. The processing itself takes part using containers. This is why we also need a container registry. And then the results are either processed further with tools like Power BI or maybe QGIS or whatever. So the basic idea from Azure Space for Orbital Analytics was, okay, let's make it easy for everyone. So what they said, okay, let's provide some basic tools for handling of geospatial data, you know, transforming from one file format to the other, or cropping, tiling, stitching, and so on. Which in turn means that AI providers like us at Black Shark, we can focus on our models or on our computer vision algorithms and so on. And the customers, typically you, are the ones who are able to build ready-made workflows with all of the plumbing taken care of. So just to give you an idea why the plumbing is necessary, let's assume we have a source image, but the source image is too large for the algorithm to handle. Then we're using one of the provided activities, which, for example, tile this image into smaller parts. Then we are running our model on each of these 9 smaller images, producing 9 results. And then we use another ready-made tool for stitching the results together again. And the second idea was they said they would like to be as open as possible. So they don't want anyone to force into using Synapse, Spark, what have you. So they said, okay, the most generic thing we're able to think of is a Docker container and starting through command line parameters. And actually, this is what they're doing. The drawback, of course, is Synapse Spark does not really handle containers. I mean, you're able to maybe convince it, but it's not a nice way. So they said, okay, let's use Azure Batch. And for this, there is this Synapse activity where you're able to launch Azure Batch tasks. So let's have a short look at their workflow. Basically, they have divided this into 2 sub workflows, one for the initial transformation, and then one where you're actually doing your CV algorithms or AI algorithms. So maybe let's first have a look at the transform. Let's see if I'm able to. And it starts off with that it's reading out which files should be processed. And if we have a look at the if we have a look at the settings, this is exactly what I've just shown you before. There is a linked data set, and we're reading out the child items. Then we're basically processing the names. Basically, what it does is, as a preparation for the handling afterwards, it adds all of the file names to a single string separated by a comma, which is actually a little bit more complex than it needs to be. And then there is the question: do we have more than one geotiff? Because if yes, then it needs to do some internal stuff, what the source and destination directories are. And then, for example, it has Spark job definitions of how to crop something. And the Spark job basically just executes a Python file. And this crop, then, the Python file is reading the images, doing the necessary transformation. Here, it's a crop, and from there, it's moving on. Then it's so converting everything to a PNG. As you see, for example, here, the source folder name then is crop. And then eventually it does the necessary tiling. And for example, here in this settings, you see that it's doing this split, which I've shown you on the slides, so that the individual tile is only 512 by 512 pixels. So basically, this is a long way of saying list of all of the files I would like to process. If there are multiple files, do some background stuff, then crop it to the defined area, maybe do some file conversion, then split it up so that the later steps are able to do the necessary processing. So with this, the transform step is done. And then we are here with the actual Azure Computer Vision workflow. And maybe the most interesting stuff here really is this spec document. I'm just going to show you the one which they have provided in their reference architecture, which is this spec here. Let's make this a little bit larger, where basically what you do is you say, okay, the necessary container, so can be found here. Or for example, I need at least 14 gigabytes of memory and 3 CPUs, and I want my data mounted into this directory over here. So this is what the spec document is all about. Then it's the tiles right now are residing on a blob storage account. And the idea of them was the most generic stuff, because if you need to access blob storage, which means it's already Azure specific, let's have the files mounted inside the container, meaning here they're transferring the files from the blob storage to a file share, and then from the file share, they are mounting it into the container. Because initially they had some problems with this custom activity. They're actually using a web activity to launch the Azure Batch stuff, which you're able to see here. So they're doing a real post to this URL over here, which is, batch azure dot blah blah blah. And then, of course, as they are not using a ready-made activity, they just make a post to the REST API. Afterwards, they have to wait by querying the REST API again until this batch job finishes. And then they so copy the data back to the blob storage account, where there is another Spark job doing the final polishing. And this is the way they envision that you're able to process terabytes or even petabytes of data. Just to give you a short look at what it looks like for our container, which is, I think the file share is here, right? Inside the file share, we have information about some of the parameters. We have a test.tif, which is the input file format. This is a geotiff, which is not your TIFF you may know from fax or whatever, but actually it's a highly optimized format for geo-referenced data. And once our Azure container runs, it produces building footprints as raster mask and also as vector information. Maybe to show you what this looks like. This is the wrong project. Sorry. This is the TIFF, which is about 11 megabytes, typical view from above. And what our model then does is it marks all of the buildings. White means there is a very high probability of a building, and the reddish outlines means there is less probability of a building. If you're very sharp-eyed, you see that especially the buildings on the border are not actually detected very well. And the reason is the AI model needs a certain size to make detections viable. And at the border, usually there are some issues. And the geo package then just makes some outlines. So it says this now is vector data, whereas the previous mask was still pixels. This is actual geometry vector data. And you're also able, what was on the screen before was, I think, this one here, which is, for example, these are the footprints we have been detecting, but we're also able to do, let's say, higher regularization, where we're trying, that every building has a straight line, right angles, and so on and so forth. Or, for example, we're also able to detect vegetation. And these are then the results which either you or someone else is using for so later on to achieve whatever they set out to achieve. Behind the scenes, because we're already a little bit late in time, I'm going to skip this detailed diagram, which I've more or less already talked about, and talk a little bit about the lessons learned. One thing which I didn't show you is all of the logging and monitoring. On the one hand, Synapse provides very nice so capabilities. On the other hand, the error messages are not always helpful. And especially if you're dealing with Azure Batch, all of the log messages there are actually in the batch service or stored away in some storage account. So probably what you would like to do is have app insights or whatever. Otherwise, debugging might be a little bit cumbersome. Resources, when you're doing a lot of downloading, uploading, and similar, if you're not choosing the right size, your workflow actually becomes I/O bound. So your nodes are twiddling their thumbs. So it needs some tweaking so that you're not really I/O bound, but that you're using your nodes for full capability. On the plus side, Synapse is really very good at tracking costs, at least for resources managed by Synapse. So you always have an immediate feedback of how much this analysis needed. And as a side remark, like every larger system, Synapse is really big. The learning curve is okay, but if you really dig deeper into it, it still takes time, like I would say in every other field as well. So what do we do with it? So for us, this footprints, vegetation, and so on is only the first step. We do some additional geometry detection and then 3D reconstruction to eventually be able to have a 3D world like this, or more like this if we do a rendering inside a game engine like Unreal or whatever. So for example, what you see here, the building footprints were exactly detected the way I told you. The building heights used different algorithm, and then we made a 3D visualization where the facades, because we don't see them, are plausible. So they're made up, but they're geotypical for this area. And then it looks very nice if you don't know the city exactly. But if you know the city, you would say, but this place over here doesn't have white walls, but yellow walls or whatever. Okay, so we're basically at the end of my presentation. If you're interested, hop over to GitHub, where you're able to see the reference architecture in its full glory. If you would like to play with one of our containers, then you're able to go to, where is my, there. You're able to go to our site over here, where we tell you what you're able to use right now, building and vegetation, and where we also have a user guide on how to set this up. Okay, so that's all I had. I hope it was interesting to you, and thank you for watching. Any questions? If not, then I will hang out in one of the chat rooms. So if you'd like to talk to me, just contact me. So thank you very much. Have a nice rest of the day and a nice weekend.